All right, chapters 25 and 26 in our textbook about fluoro. We'll talk about why these images of the structures of the eye are important, how image intensification occurs. We'll talk about flux and brightness gain. And then really the big thing is I just want you to understand the big difference between conventional fluoro and digital. Okay? So structures of the eye. Why do we need to know this? Well, because interestingly enough, the way the eye works is exactly the way the fluoro tube works. Right? That's why he stresses all this stuff about the way the eye works. The way the eye works is it has a lens up here in the front, right? It actually inverts things and points them to a certain area here in the back, right? So like they talk about babies when they're first born, they see everything upside down until their brain figures out how to turn it around and make it right side up, right? Why does the eye flip things around like that? Well, because it's intensifying what it's seeing in order to better perceive it. That's why he goes into this high school explanation of how eyes work. It's because because this thing works exactly the same. It takes a certain amount of stuff, flips it around upside down in order to intensify it. So when we're talking about you'll notice there's some similar terms here between the workings of this image intensification tube and the X-ray tube. The main one I want to point out is this focal point. It is a totally different term when we're talking about fluoroscopy because the focal point is the point at which things are flipped upside down. So everything's directed towards this focal point, and depending on where that focal point lies, that's how it magnifies things. That's how it changes brightness. Okay? So we've got this input phosphor over here that when the X-rays hit it, they've got cesium iodine inside of them. They're going to fluoresce. And they're going to strike this plate here that's going to emit electrons, right? And those electrons are going to be directed towards a focal point where they cross in order to intensify them at this output phosphor. Two things that are really, really significant here is we have a cathode and an anode, right? So it is similar to an X-ray tube, right? It has a cathode and an anode. Right? It's emitting electrons and it's attracting those electrons. But the point of it doing now is it wants to intensify a signal. Okay? So let's talk about what's happening when it intensifies that signal. It has what's called flux gain. And so that's going to be equal to the number of output light photons that are produced by the intensification tube divided by the number that came in. And it will always be more. Right? It will always be more because that's why we're doing this. It's an intensification tube. Interestingly enough, the brightness gain down here, I don't want to move off the slide until we point this out. Brightness gain is going to be equal to how small it makes this thing. So the smaller it makes it, the more bright it will get. The smaller it makes it, the more bright it will get. So this is helpful for us because at times when we're using the fluoro machine, we might want to get a bigger picture, right? And they probably magnify things in a limited degree in fluoro. Well, why don't they do it more often? Because, it would be helpful to have things magnified, right? You'll notice that anytime we use the magnification, what we're shifting is this focal spot inside of the tube. We're just shifting that focal spot back or forth, right? So that will provide, magnification mode is going to give us better spatial resolution. It's going to give us better contrast resolution, but it's also going to equate to a higher patient dose because the machine's going to have to compensate for that by increasing the amount of X-rays it's sending to the patient. Talked about with conventional fluoro, one of the main differences between conventional and digital is the amount of mass that's being delivered to the patient. With conventional fluoro, we're probably talking about an MA of like 5. An MA of like 5 in conventional, right? 5 MA. So we'll have to bump that up in order to magnify things. So then once it's intensified this signal, it's going to feed that signal into what we call a television camera, right? And it works very similar to that tube television I have back there in that it has a tube, it has an electron gun. So visible light is coming into it here, and this is from that intensification tube. And then it has an electron gun that's scanning over that right here. It's scanning over it and it's producing a signal. That's all we need to know about this goofy television tube. Is it's a TV camera. It's just using an electron scanner to scan a light signal. Right? Again, the reason that the board likes us to talk about this stuff, or the reason it's important, is number one, it has a glass envelope. It is, again, it has that anode and cathode type setup. So pretty much everything that goes into the fluoroscope works a lot like an X-ray tube. We're just using it differently, right? We're no longer using it to produce X-rays. We're using it to produce a video signal. So we might also feed that into some kind of fiber optic lens, right? So we could have a number of different things that's occurring. Like these older conventional fluoroscopes, they could have a TV camera. You could take a spot film with them. You could divert this image signal in a number of different directions. And that's all this is trying to point out to us, is that some of these things were devised just to have a TV camera. Some of them had beam splitting, where you could say, hey, I want the image monitor, now I want you to take a spot film. So when we're saving spot films, it's just using a mirror to put those light signals in different directions. Okay? So all this image is talking about. This is really all this textbook chapter is talking about. It just chooses kind of a goofy way to talk about it. The final thing is this, which is totally obsolete. I just want to stress to you how obsolete this is. This is an old tube television, right, which we no longer use, right? But it is interesting to note that it has, again, an anode and a cathode or an electron gun. So again, it functions somewhat like an X-ray tube. So we've talked a little bit about digital fluoroscopy. Another thing that's important to consider with this thing is patient dose, because the main area of patient dose for us as conventional X-ray techs will be our fluoro patients. They are receiving the highest dose, right? So what's normal for a entrance skin exposure, that's what that ESE means, entrance skin exposure for a fluoroscopy exam. This is about 10 Rankins per minute. 10 Rankins per minute. So every minute of conventional fluoro, about 10 Rankins per minute. And interventional, where they're using magnification, well, guess what? It's more. Interventional, they're trying to look at vessels of the heart, so they're using magnification mode a lot, so therefore the dose is higher, right? Anytime we do a spot film, it will cause an increase in patient dose because it's now applying more technique through the fluoroscope, okay? And the automatic brightness control is kind of our friend. It's constantly toggling things inside. It's upping and lowering dose in order to control brightness of the image. Okay? So this is the, it just says evaluate annually. That means that we need to look at this thing. The physics guys will come in, look at that automatic brightness control, make sure that it's operating appropriately, because if it's not, guess what? The patient's dose is higher and so is yours, right? Now, digital fluoro. Let's compare and contrast it some with what I just talked about with conventional fluoro. We'll talk about the advantages of the CCD, and then we'll discuss differences in image display, because this is kind of where things are at. This is the state of the art. So, what's interesting between digital and conventional, right, is that with conventional, I said the MA would be like 5. Over here in digital, the MA might be more like 100, right? But look at the dose. The dose is like half, right? How do we account for that? We'll talk about that here in a minute. But primarily what the digital is doing is it's pulsing. So it has a higher MA, but it's pulsing it. It doesn't have as high a seconds, right? It's pulsing that energy in order to capture the image. Spot films with digital, it's going to be a lower dose than spot films with conventional, just because of the way that digital samples. Okay? Magnification mode with digital is going to be less than magnification mode with conventional. So on the whole, digital comes out on top. And the reason it comes out on top is because of these things, CCDs, charge coupled devices. Now, we're going to get very in-depth on these things. We're going to spend a whole trimester talking about charge-coupled devices. So I've only got one slide here, but I want you to be aware of this because it's driving where things are at. This is why all your facilities are changing over to digital. is because these things have the potential to reduce patient dose significantly, like I just pointed out. But at the same time, we need to know how they work. And historically, people have not been really good about educating themselves on these things. So in this case, we still have the light from an image intensifier, right? But instead of being directed through a tube where it's flipped upside down in order to intensify it, it interacts with light inside of a semiconductor. So it knocks electrons around inside of a semiconductor, and that's how it processes the signal. This is a digital process, again, because I said it has integrated circuits in it, right? It got rid of the tube, and in its place it put a computer circuit, right? So this semiconductor here is going to be bouncing electrons off of a positively charged pixel, right? And the size of this pixel is going to determine how nice the picture is. So these pixels need to be really, really small, right? And then once that pixel receives a signal, it gives that signal then to this thin film transistor, right? And that's what's then sent to the computer, right? So there's no cameras in this, right? There's no need to flip things around in order to intensify brightness, right? It is just now a digital signal. So why do we do all this? What's the point? Well, because we're not using this vacuous tube to do this, we're going to have a higher spatial resolution. We'll talk more about what that means, but basically a crisper picture, right? We're going to have a higher signal-to-noise ratio, which is good. There's more signal than there is noise, okay? Higher detective quantum efficiency. What the heck is that talking about? Well, I don't want to get really in depth on that right now, but basically it's more efficient. It's more efficient than the old school way. There's no warm-up required. There's no lag or bloom around like metal. It doesn't have spatial distortion. We noticed that that magnification tube was like kind of had a slight curve shape to it that could distort things. And it's unaffected by magnetic fields, right? So it results primarily, the big thing driving all this, lower patient dose. And this is why the federal government's creating all these laws saying everyone needs to switch over to digital, is because primarily it can result in a lower patient dose if we use it appropriately. So the big thing here, just again, a final comparison and contrast between digital and conventional is the conventional mode is going to use this interlaced mode, and I don't expect you to understand all that works, but it's an old school television thing, right? And the big thing here is the signal-to-noise ratio is like 200 to 1. We get 200 signals to every 1 incidence of noise, right? So it's fairly good, but there's still some noise there. Versus digital, it's using progressive scan, which is a digital sampling process, digital display process. You don't need to know that really in depth right now. The big thing here is, I don't expect you to know these numbers, is the signal-to-noise ratio of digital is much higher, and that's a good thing because it means that there's much more signal than there is noise.